Now we discuss about IEEE 754 floating point representation. What is IEEE 754 single precision floating point representation of the decimal point 0.7425? The actual answer is this 0, 1, 1, 1, 1, this, and this. Because in the single precision format is the binary 32 bits represent a floating point number. Here, three primary components: the single bit, this 0, this denotes for sign if positive integer, this is 0, and if the number is negative, then this is 1. Actually, this minus 1 to the power 0 for positive integer and minus 1 to the power 1 for negative integer. Actually, this minus 1 to the power 1 equal to minus 1. So this is the 1 for negative integer and 0 for positive integer. Here this number is positive number, so this is 0. And this blue color, this is exponent part for this bias exponent for 8 bits, reserved 8 bits. And next, this 23 bits for the mantissa, that is the fraction part of the number in decimal expression. This is a sign bit S, and this is the exponent, this bias exponent 8 bits, and this is the mantissa fraction part 23 bits with one implicit leading bit. Actually, this integer part 1, this is the implicit, this is the conceal, and this 23 bits only explicitly stored here, this for mantissa part fraction part. Now this sign bit, obviously this is the positive integer for sign bit is 0, minus 1 to the power 0, so this is 0. Now we convert the decimal number 0.7425 to binary number. For this, we multiply this number by 2, we get 1.485, and here the integer part is 1 and the fraction part is 0.48. So store this integer part 1, and next step, multiply with 2 with this fraction part, and next 0.97, so store this 0 is integer part and this 0.97 in the third step, and in this way so on. So for this we get 1 0 0 1, and this ultimately is the continuing. Actually, this is the and dot here, so we get this decimal number, this is the 0.1. Actually, this is the decimal 0.1, this 0 1 1 1, so 0 1 1 1, and this is the next, and this is the binary number in this. Now we want to normalize this binary number, shift the binary point, so only one non-zero digit is to the left. So here the integer part is 0. I want to get this in this integer part only single digit 1. For binary expression is the 0 and 1 only, so integer part is only 1 here. So for that, so here this 1.011 and so on. So we multiply by 2 to the power -1, because this decimal actually, sorry, this is the radix point, actually the binary point here, not decimal point. This is the radix point, actually here the binary point, shift to the left. So this is the radix base is 2, so 2 to the power -1. If is this decimal number, then 10 to the power -1. This is the decimal, if this is decimal point. But here this is the binary number, so this point is binary point. And so after shifting this the decimal binary point to the left place, so we multiply by 2 to the power -1. Now we calculate the biased exponent. Here the exponent part is -1. This actual exponent as 8-bit exponent for single precision. So bias is the 2 to the power n minus 1 minus 1. This is the formula for bias. Here 8-bit exponent. So value of n is 8. So this 2 to the power 8 minus 1, that actually 2 to the power 7, 128 minus 1, this is equal to 127. So bias exponent, actually this is the bias plus exponent. Here bias for 8-bit is 127, exponent is -1, so actually this is the 126. This is the biased exponent. Now we convert this biased exponent uh, in 8-bit binary number. So this is the integer 126 in decimal. So 126 divided by 2, we get 63. This is the quotient, and remainder is 0. And again divide by 2, this is the quotient 31, remainder is 1, and so on. This last, this is the 1. So dividing by 2, so 2 into 0, this is 0, so remainder is 1. And from lower to upper for this integer part, so 8-bit biased exponent is given by this decimal number 126 equal to, so this 8-bit, so this 0 1 1 1 1 1 1 0. This is the decimal expression. This, so this part is the biased exponent for this blue color, this exponent, bias exponent. Next, to identify the mantissa part, actually this is the floating point. This representation is from the standard binary number. So this is the floating point, this 0 triple 1 1 1 double 0 double 0 1 0 1 triple 0 1 1 1 1 0 1 0 1, and so on, dot 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 dot. So mantissa part this, the 24th bit, actually this is the, we accept only 23 bits. Here 23 bits for that. This the 4 4 8 4 12 4 16 4 20, and this 0 1 1, 23 bits. Actually this one is padded by the rounding rule. Rounding rule, this actually this is the from the standard 1 2 3 4 5, and for this 0 1 0, so this 0 1 0 1, and so on. So there may be non-zero digit after that, so we get only this 0. So add 1 at this point. Actually the rounding up rule for this binary expression, binary number, is round down. If the first bit after nth place is 0, discard it and all subsequent bits truncated. Actually, this is the this number 0.10011. This rounded to 2 bits. So this 0. So this up to this next bit is 0. We want to preserve here 1 and 0, 0.10. So this 0, so only rounded down, truncated, and the first bit, this 0, after the first bit, this 0, so in it plus 0, discard it and subsequent bits truncated. And if this next bit 1, next bit 1, and followed by a non-zero bit 1, 1. So rounded up, add 1. So this 1 plus 1, this equals to 0, and carry on 1. So this 1. So this 1. So this one, add 1 to this place, and so this 1 plus 1 0, and this is the 1 plus 0 carry 1, so this is the 0.11. And next, tie breaking, that is ties to even, if the first bit after the nth place is 1, this 1 0 after nth place, after 2 bits, this 1, and following bits are 0, check the nth bit, the last bit, to keep. If nth bit is 0 even, nth bit is 0 even, actually here second bit is 0 even, and round it down. So we just uh, truncated is this 1, and all bits are after that one, all bits are 0. This is the, if the first bit after nth place is 1, this 1, but all following bits are 0. So this is the up to 2 bits, this 0. So 1 0, down to this. If nth bit is 1, nth bit is 1, here second bit is 1, and rounded up to add, to make it even, make it even. So 1 plus 1, this is 0, 0, 1 plus 1 0, carry 1, this 1 plus 1 0, carry 1, so this 1.00, this is the actually the rounding rule for binary number. So this is the 23 bit for Mantis part, floating part, but for this integer part, this standard normal standard binary, this in one integer part, there is no mention for this integer part in the IEEE 754 single precision floating point format of this. If you're interested, then IEEE for Institute of Electrical and Electronics Engineers. Please click on the link. So we get this website IEEE numeral system. This is the first, choose this decimal to IEEE 754, and next choose, you can choose either IEEE 754 2 decimal. So first we choose this. uh, you can choose 16 bits, 32 bits, so you choose 32 bits. This 0.7425, 7425 here, calculate this. So this we get this number, floating point representation, and calculation path, this sign bit, fraction part convert to decimal, sorry, decimal to binary, and this shift the binary point. Actually this is the normalization, and calculate the exponent, bias exponent is -1, and finally we get the answer, this. Thank you for watching this video.